Hey dudes and dudettes, are you ready for some differential equations? Oh, this is way too fun. Okay, so we're going to talk about section 2.1, which is all about first order linear equations. Let's try to take a second and try to think back to our discussion on Wednesday and remember what we mean by a first order linear equation. It should be a differential equation that can be written in this form. Okay, it's first order because we only see a first derivative. We don't, oh, oops, I'm missing something here. Should be p of x times y. Yeah, so it's first order because we only have a first derivative. We don't have any second or higher derivatives in this equation. And it's linear because the derivative of y and y itself are not being plugged into any other functions. Yes, we have arbitrary functions here for the coefficient of y and for the function over here on the right-hand side. Now, speaking of that function, if this is just an arbitrary, so this can be any function, if this is equal to 0, and by equal to 0, I mean 0 everywhere, so I'm going to write equal sign with 3 lines. That means identically 0. It's 0 for all x, not just for one value of x or whatever. So if f of x is the 0 function, then the equation is called homogeneous. Okay, that's the definition here. Our equation is homogeneous if we have something on the left-hand side and it equals 0. If f of x is anything else, any other function, then it would be called non-homogeneous. And actually, we're going to split section 2.1 into 2 different lectures. Today, we are only going to be talking about homogeneous equations. So let's start looking at some examples. The goal for today is going to be to understand how to solve any homogeneous first order linear equation. It's kind of like the basic differential equation problem, the basic initial value problem. Okay, so let's see. Let's say I have this initial value problem. Now remember, initial value problems, they always come with 2 things. 2 things are given to you. One is the differential equation, and in this case, we're going to make it y prime minus ay equals 0. So that is, because that's a 0 on the right-hand side, this is a homogeneous equation. And we're going to have an initial condition. And we're going to say that y of 0 equals 4. Okay, now, you'll notice that this differential equation can be rewritten as y prime equals ay. And by the way, a is just a constant here. And we've seen this before. On the very first day of class, this was our exponential growth model. And it's not too hard to be able to solve this by inspection, meaning that you don't actually need to go through any kind of algorithm or idea here. You can just kind of think about derivatives that you know and find a function that behaves this way when you take the derivative. So we could say that y of x equals e to the ax. And actually, remember, if this is going to be a general solution, then I'm going to, I'll just get rid of this x. throw this constant c out in front. Now that's great. That works. If you can solve if a differential equation is easy enough for you to solve by inspection, then great. Do it. Whatever. Who cares? But that's not what we're trying to learn about today. So I'm going to go through a different way. Maybe if you can't, if you have a hard time seeing that that function is a solution to this equation without any other information, here's the idea. Here's the process that you would go through to try to solve it. So I'm going to mess around with this equation a little bit, and here I need a little bit of board space, so I'm going to erase the initial condition for now, but we'll bring it back later. If I mess around with this a little bit, I can get y prime over y equals a. Now you might be a little bit wary about having y prime divided by y, because what if y is a function that equals 0 somewhere? And yes, that is a valid concern. However, when we go through this process this way, everything works out. And we're not going to really worry about that too much right now. Now, if I gave you this equation and I asked you to solve for y, what would you do? Well, you would probably see this derivative right here and say, I want to get rid of that derivative somehow. So let's try to integrate here. So if I take the integral of both sides, it's going to look something like this. Okay, now that right-hand side is easy. The right-hand side should give me ax plus c, right? The plus c is what we always get when we're doing indefinite integrals like this. What about the left-hand side? Well, you can use substitution tricks here. If you set u equal to y of x, and that means that du dx is going to equal y prime. Or actually, sorry, a better way to write this is du equals y prime dx, which you get from taking the derivative of this side with respect to x. The chain rule brings that dx out to the side. So now, when we make this u substitution, we have this integral turns into 1 over u du. And the antiderivative of 1 over u, of course, is natural log of the absolute value of u plus c. And but we probably want this in terms of y and or x, and that means that we're going to instead write this as natural log of the absolute value of y plus c. All right. So let's see. I'm going to write that over here. Only instead of plus c, I'm going to write plus d, because that may not be the same as the c on the other side. Now, in differential equations, there's always a lot of we deal with constants very loosely. Let me put it like that. Meaning that I am just going to erase that d right there. Now you're saying, oh, you need a constant there because you have an indefinite integral here. Well, the thing is, that's just an arbitrary constant. I also have an arbitrary constant on the right-hand side. So what I could do is move the minus d over, or subtract d from both sides once I have that d. But really, c minus d, if these are both arbitrary constants, then c minus d is also an arbitrary constant. So let's just take that and call it c. And we end up with that. Okay? That might be a little bit confusing at first, but just think of it as, in terms of arbitrary constants. C minus d is just as arbitrary as c or d, and so we might as well move all the constants to one side and just absorb them all into one arbitrary constant. Okay, now from this point, we're going to I want to isolate y, right? Because the goal here is to solve for y. We're going to take the exponential of both sides, raise both sides as an exponent of e. Now that's going to cancel out with the natural log, which is why we're doing it in the first place. And on this side, I'm going to get e to the ax plus c. Now, I can also just get rid of these absolute values. No, this absolute value. There we go, singular. I can get rid of that because on the right-hand side, this is always going to be positive anyway. So if I just let y equal that, then it's always positive and we're happy. Okay, now you might say, well, this looks a little bit different than the function that we had before. What's the difference? Well, now we have a plus c up here rather than before. Well, it may look different, but it's not different. And the reason is, from the laws of exponentiation, we could separate this into e to the ax times e to the c, right? But what is e to the c? Well, c is an arbitrary constant. E is a, it's a defined constant parameter, whatever. And e to the c, well, that's just an arbitrary constant. So what am I going to do? I'm going to take that e to the c and just rename it as c again. So this is a different c technically, but it's still, the constant was, c was already an arbitrary thing that I knew nothing about. And so now this new c is still just a constant that I know nothing about as well. And might as well just call it c. C is, so this sort of hand wavy stuff where c is changing values as we go. This is just something that we do in differential equations. So get used to it. All right. But we're not done, right? Because even though at this point, this is my general solution of the differential equation, I don't know what c is now, but remember, I use my initial value to figure out what c needs to be. And the initial value that was given to us is that y of 0 needs to equal 4. Okay? Well, y of 0, that equals c times e to the a times 0, and which is c times e to the 0, which equals c. So that means that c has to equal 4. And finally, the solution to my differential equation, to my initial value problem, is y equals 4e to the ax. Boom. Dunzo. All right. Okay. Now, of course, this is a problem that you might have already known how to solve because we talked about solutions to this particular differential equation already. So let's see how this works for a different differential equation. Let's do something a little bit similar, but let's make it y prime plus xy equals 0. Again, it's homogeneous. Now my coefficient in front of the y term is not a constant, it's the independent variable x. And I'm just going to give this some initial condition. Let's say y of 1 equals 3. Okay? Let's do the same sort of thing that we did before. If we mess with this, we get y prime over y equals negative x. Now, let's take the antiderivative of both sides. The left-hand side, as we saw before, is going to give me natural log of absolute value of y. And what is the antiderivative of the right-hand side? Well, It's easy enough. Just doing some reverse power rule shenanigans. And we get plus c. Now, when I solve for y here, I end up with y equals again with my arbitrary constant trick, I'm going to end up with c times e to the negative 1/2 x squared. Okay, and I erased my initial condition. So now if I'll write it out again, y of 1 equals 3. And if I plug in 1 here, y of 1 equals c times e to the negative 1/2, which, another way to write this is c over the square root of e. So if I want this to equal 3, then that means that so 3 equals c over the square root of e. Solve for c, I get c equals 3 times the square root of e. So if I, now when I finish this off though, I really want to write out the whole solution. I'm going to get y of x equals 3 times the square root of e times e to the negative 1/2 x squared. There is a way to simplify this. If I were to, this is fine right here. I have my constant. It's okay. If you answered this on a test, I wouldn't take off any points. But you could simplify it, make it a little bit nicer by combining this e to the 1/2 with the e over here. Really, that's going to mean you're adding 1/2 to the exponent over here, and that can be written as this. So that's a little bit nicer way to write my solution, but it doesn't really matter. Okay, now, so really, what was the only real difference between this problem and the problem before? It was just right here. Before we had a constant there, now we have this function negative x, and as long as you know how to find an antiderivative, so you know how to integrate the function on the right-hand side at this point, you can solve any first-order linear initial value problem. Okay? So if we take these ideas and turn them into a formula, it's going to look like this. So this is a formula for the general solution, and then you would take this and use your initial value to find the value of the constant coefficient. So let's see, if y is a solution to y prime plus p of x times y equals 0, then y equals a constant times e to the negative integral of p of x dx. Okay? And now when you work on these problems, I highly suggest at least once or twice going through the full derivation like I did in these examples before you start just turning straight to the formula, just so you can get a feel for really why this works and feel a little bit more comfortable with it. But right now, I want you to pause the video and work on this practice problem. All right, let's take a look at the solution. Here's the initial value problem. I have my differential equation on top, and then my initial value condition, or my initial condition, sorry. Initial value, initial condition, but not initial value condition. That sounds too weird. Okay, now, you'll notice that this is exactly the type of first order linear homogeneous differential equation that we've been talking about. And this whole function right here is our p of x. So when we find the general solution to this differential equation using the formula that we've talked about, we'll get y of x equals a constant c times e to the, let's see, negative integral of p of x. But since p of x is already negative, then I'm just going to write the integral of x squared minus 4x plus 5, and dx. And when we solve that integral, it's just a polynomial, easiest integrals in the world. So we get 1/3 x cubed minus, not 4, 2x squared plus 5x. Now, we want to use our initial condition to solve for c, and we see that y of 2, if this is y of x, then y of 2 equals c times e to the, let's see, we're going to get 8/3 minus 8 plus 10 for a total of 8/3 plus 2, which is also known as e to the 14/3. Lovely. Now, if I want this to be equal to e, e to the 1, I'll divide both sides by e to the 14/3, which is really just the same as multiplying by e to the negative 14/3. And we see that c equals e to the 1 minus 14/3, which comes out to 11 minus 11/3. Okay, and now when you write out your solution then to the initial value problem, you could just write this in place of e and write the rest of it, or you can combine your exponents here to get e to the 1/3 x cubed minus 2x squared plus 5x minus 11/3. And you're done. That's the solution. And we are done. Wait, no we're not. Another practice problem coming right at you. All right, second practice problem. Man, this problem actually could have been a lot nastier if I had written cotangent here instead of cosine over sine of x. Cotangent, of course, looks simpler, but seeing it as cosine of x over sine of x is actually a lot nicer for integrating. Besides, if I had cotangent, the first thing I would do is turn it into cosine and sine anyway. So, all right, here we go. Let's see. The cosine over sine, that's p of x. So we get that y, the general solution of the differential equation, equals c times e to the negative integral of cosine of x over sine of x dx. Now this is actually a little bit similar to our integration that we did earlier with y prime over prime, y prime over y. And when we do this, let's see, cosine of x over sine of x dx, we'll use u substitution, setting u equal to sine of x to get, this is the integral of 1 over u times du, which of course equals the natural log of the absolute value of u plus c, and this equals the natural log of absolute value of sine of x plus c. Okay, so that then is going to be our general solution, the minus the natural log of the absolute value of sine of x plus c. Great. Oh, actually no, I don't need, forgot, I don't need the plus c there because I already have a constant right here. Now we're going to use the initial condition to see what c needs to be. So we'll take pi halves and plug it into this general solution, which will give us c times e to the negative. Okay, what is sine of pi halves? That is 1. Absolute value of 1 is, well, here, let's just, okay, absolute value of 1, of course, is 1, and natural log of 1 is 0. So that means that this is c times e to the 0, which just equals c. Cool. It might have been complicated, but it wasn't. So we're just going to set c equal to 5, and therefore our answer is 5 times e to the negative natural log of the absolute value of sine of x. And we are done. Is that our last practice problem? Yeah, it is. Okay, so let's see. That's the video. That's our lecture. It wasn't too bad. Next time, we are going to talk about non-homogeneous problems. So that's when you have a non-zero function on the right-hand side of your differential equation. It complicates things a little bit. And good luck with your homework, and I'll see you on Monday.